Welcome my friends, welcome to my next lecture. Now this lecture my plan is to talk about what is called vector line integrals. So in my last lecture I talked about scalar line integrals and then couple of properties I have discussed and then one applications I have discussed. So that's very brief about scalar line integral. And now I think I am in a position to talk about the notions of vector line integrals, at least in today's lecture. And if time permits, couple of properties and applications I will talk about that. Okay, so as I said, so I think I should start with the notions of what is called vector line integral. So that's I have written here. So vector line integral over, so smooth curve I have discussed, right? What is smooth curve, what is piecewise smooth curve in Rn, in n-dimensional Euclidean space. So once I have the notions of smooth curve or piecewise smooth curve, then I can talk about the notions of vector line integral. Now if you remember, in my last lecture when I was talking about the notions of scalar line integral, and I said that you start with a functions which is taking scalar value, okay. So that means it's kind of scalar field and give the notions of integral in terms of partitions, then you see the corresponding integral is called scalar line integral. Now from there you can easily guess, if I want to talk about vector line integral, then instead of scalar valued functions then you have to take a vector valued functions, or that means vector field. And then you give a meaning of like vector line integral. So that is the kind of intuitive idea, okay. So this is like vector line integrals. Before that I need a little bit of what do I mean by closed curve, simple curve and simple closed curve or contour. So what is the first definition? It is a closed curve. So I think these notions I already discussed at the beginning of my lecture. Lecture means when the course started. However, I am just once again recall few of them. So what is that? The first one is the closed curve. So what is closed curve? So a curve C, and once I have a curve, so that means I want to talk about curve in Rn, that means it will have a parameterizations. So R, capital R, it will be mapped from some interval subset of R to Rn if I want to talk about curve in Rn, okay. So a curve C with parameterizations Rt, where T running over the closed interval A to B is said to be a closed curve. See, if I have a parameterizations capital R of my curve C, what is the starting point? That means in the n-dimensional Euclidean space, it is a curve with starting point is Ra and ending point is Rb, something like that, okay. So this is Rb and this is Ra, and corresponding natural orientation you will have. Anyhow, I will talk about that, more on that later on. So this is the initial point, this is the final point. So closed curve means Ra should be exactly equal to Rb. So that is the definitions. So a curve C with parameterizations Rt is said to be a closed curve if Ra is equal to Rb. For example, if I start from here, I will come back here itself. That means Ra should be exactly equal to Rb. That is the definition of closed curve. For example, circle, you can take the circle. So circle means cosine t, sine t. That is the parameterizations R, capital R of t. So you can write it capital R of t, which is nothing but cosine t comma sine t, where t running from 0 to 2 pi. Okay. So now you see what is R of 0 is exactly equal to what? So R of 0 is nothing but 1 comma 0, which is same as R of 2 pi. Okay. So this is same. So R of 0 is exactly equal to R of 2 pi. So therefore this curve is called a closed curve. So that means if I draw a picture, it will be like this one. So I am starting from here, I am going here and I am coming back here. This is the kind of circle, it is a closed curve. What is the definition of simple curve? Simple curve means a curve C with the parameterizations R of t, t running from closed interval A to B, it is said to be simple. The definition is that R, capital R should be injective except the two endpoints. So that means except A and B, so that means Rt1, if T1 is strictly less than T2 and T1 value is greater equal to A and T2 is lesser equal to B, that means Rt1 is not equal to Rt2. That is called simple curve. So simple curve means R is injective, I should say. That means take 2 points T1, T2 in the interval closed interval A to B, and suppose T1 is not equal to T2, then Rt1 should not equal to R of T2. So that means take T1 comma T2 belongs to closed interval AB such that T1 is less than T2, then the corresponding value of Rt1 is not equal to R of T2. If this is the case, then I will say that my curve is injective. For example, this is injective curve. Circle, this is injective. That means there should not be any kind of cross kind of things, okay. So that means there should not, your curve should not have this kind of things, like not this kind of things. Here you will have what is called injectiveness break, Okay, you should not have or like 8 figure, you should not have 8 figure kind of things in your curve. That is called simple curve. Okay, there should not be any cross. So, for example, circle there is no cross. So, this is a actually simple curve as well as it is closed, that means a simple closed curve. Okay, this is not simple. So, if I have a curve like this one, so this is not, this is the disturbing point where you lose the injectivity of your capital R. Okay. And what is simple closed curve? You just combine the first two definitions. That means if I have a curve C with parameterizations RT, it's said to be simple closed curve. First of all, it should be injective. Okay, so that means if I take any 2 points T1, T2 in the open interval, right? This time I am taking T1, T2 in open interval AB, such that RT1 is not equal to RT2, but I want that end point, initial point and final point should be same. That means RA is equal to RB. So, that means it is closed since it is R of A is equal to R of B. It is injective because I am taking any 2 points T1, T2 in the open interval A to B such that T1 is not equal to T2, then corresponding RT1 is not equal to T2. Example, again take a circle. So, this is a simple closed curve. So, it is the starting point. I am coming here. So, it is closed as well as it is injective. That means, if I take any 2 points T1, T2 say in the open interval 0 to 2 pi with T1 not equal to T2, you see the corresponding. So, if I take T1 is if I take T1 some point open interval 0 to 2 pi, you will have some point RT1, right, and T1 not equal to T2 means you will have some RT2. So, that means always RT1 is not equal to RT2. So, therefore, this kind of curve is called simple closed curve. So, it should be simple as well as it needs to be closed. So, those kind of curve is called simple closed curve. So, now I want to define what is called smooth curve. Okay, what is the meaning of smooth curve? So, this is my definitions. A curve C with my parameterizations capital R of T is said to be smooth, very nice, it is a smooth curve. So, if the following two conditions satisfied. What about the first condition is that the parameterizations I am taking R, it should be differentiable. That means, R prime T exists. Okay, not only that, derivative should be continuous, it should be continuous. That means, R should be in C1, that means if you remember the notation C1, C1 means it is differentiable, not only that derivative is also continuous. That is the first condition. And second condition, derivative should be non-zero for all T in the open interval AB. That means, R prime T should be non-zero. If a curve with parameterizations capital R satisfies these two properties, then I will say that my curve is a smooth curve. Okay. So, of course, again you can take the circle, okay, with the parameterizations capital R of T is equal to, as I already said, so like cosine T comma sine T, the circle with unit radius, right, and T running from closed interval 0 to 2 pi. You see, this is a smooth curve. Why? First of all, of course, it is a, what is the parameterization? This is my parameterization, right, cosine T comma sine T. Of course, it is differentiable if you remember, that means it has two components. R is differentiable if and only if each component functions are differentiable. I talked about when I talked about the notions of differentiability of functions from R to Rn, that means vector valued functions of real variable. That time I said that if a function f has n many components, if a function f is differentiable if and only if each of the component is a differentiable functions. Now, this is a nice functions, each component functions are cosine function and sine function, this is infinitely many times differentiable. So, therefore, derivative exists, and not only that, what is the derivative? If I take the cosine derivative, so this should be minus sine T, and what is the sine derivative? It should be cosine of T. Again, it is a sine cosine function, so derivative is also continuous. So, therefore, first condition satisfies, and of course, R prime T, this is R prime T minus sine T cosine T, and if T runs from 0 to 2 pi, okay, open interval 0 to 2 pi, this R prime T is non-zero, at least one of the component always will be non-zero. So, therefore, it satisfies these two properties. So, therefore, circle is a what is called smooth curve. Now, once I have the notions of smooth curve, for a smooth curve, I can talk about what is called unit tangent vector. So, that means at each point, for example, if I take a circle, at each point you have the notions of what is called tangent at this point, right, some concept of tangent. Okay. So, at each point, and what is the tangent vector if you remember? So, tangent vector is T, I am denoting as capital T of T, which is nothing but the derivative the capital R prime T divided by mod or norm, you can say about the norm of R prime. So, unit tangent vector. Okay. So, tangent vector means what? If I take a point, the derivative will give you the tangent vector, that is nothing but R prime of T, capital R prime of T, and if I want to talk about unit tangent vector, you just divide it by norm of r prime t. Okay, so that is exactly the case. So this is well defined. Now you see this is well defined. Why? Because I assume that r prime t is non-zero. So therefore you can take the what is called divided by norm of r prime t, and r prime t exists. So and not only that, r prime is continuous. So that means this tangent vector actually varies continuously. That's exactly I have written, as t varies from a to b, t varies continuously. Why? Because what is your capital T of t functions? It is nothing but r prime t divided by norm of r prime t, and r prime t is exist, and not only that, it is also continuous. So therefore since r prime t is continuous, so therefore t actually, if t varies from a to b, the tangent vector capital T of small t varies actually continuously. Okay. So there is another definition that is called contour. So it says that a piecewise smooth curve. So what is piecewise smooth curve? That means it is not smooth fully, but it is the finite combinations or finite union of smooth curve. That means I can lose the smoothness at finitely many points. So a piecewise smooth curve, or sometimes it is called a contour, is a curve consisting of finite number of smooth curves joined end to end. That means if I have C1, C2, Cn, the smooth curve, maybe you can think about that the end point of C1 should be the initial point of C2, end point of C2 is the initial point of C3, so on and so forth. If that is the case, then I am saying that this is a piecewise smooth curve or contour. Okay. So now I have the notions of closed curve, simple closed curve, and then I have the notions of smooth curve, and then I have the notions of what is called piecewise smooth curve or contour. Okay. So now once I have everything, so now okay, so before defining vector line integrals, let me talk about little bit about what is called orientations. Okay. So what is orientations? So that's the heading. So orientation is that, suppose I am starting with a curve. So let C be a piecewise smooth curve, and suppose your parameterization is capital R of t. Okay. Now if t increases from a to b, that means t varies from a, starting from a and going to b, the points r of t moves continuously from Ra to Rb. Of course, I just say that if I have a smooth curve, I can talk about the unit tangent vector, and that is also very smoothly as t increases from a to b. So therefore Rt moves continuously from Ra to Rb in a specific direction, which we indicate by drawing arrows along the curve C. Okay. This direction is called the orientations, or I will say that natural orientation. That means given a curve with a parameterizations, whatever directions it will give, that is called the natural orientations of this curve, induced by the parameterizations Rt, t running from A to B. A piecewise smooth curve or smooth curve C with an orientation induced by parameterization is called the oriented or directed curve. Okay. So I think orientation is clear. So if I have a curve C is given in some n-dimensional Euclidean space, it will have a parameterizations, and that parameterizations, if t varies from A to B, okay, if I have a smooth curve in Rn and the corresponding parameterization is capital R. So if t varies from A to B, increases from A to B, then R of t, it should varies in the curve, in the n-dimensional Euclidean space, and it will follow some path or some directions. So that I am talking about the what is called orientation or natural orientations. For example, if I talk about say circle in R2, so that means what is the map? So map is that R of t, which is again cosine t comma sin t, right? Say t runs from 0 to 2 pi. So that means I am talking about a curve, that means which is circle in R2, because this is in R2, right? So what is this? This is the point. Okay. So now look, if t is equal to 0, then what is my point R of 0? So this is nothing but 1 comma 0. That means this is my point 1 comma 0. Okay. Now as I approaches, so that means the t running from 0 to 2 pi. So that means if I take t is equal to pi by 2. Okay. So then what value it will take? So R of pi by 2 should be which point? Cos pi by 2 comma sin pi by 2. So that means it should be cos pi by 2 is 0, sin 90 is 1. That means I will have this point 0 comma 1. So that means it's a circle. So that means I am starting from here and I am moving in these directions. Okay. And finally, so that means the natural orientation is this one, from 0 to 2 pi. Okay. So if t runs from 0 to 2 pi, I am starting from the point 1 comma 0, I am going in these directions and coming back to this point, and this is the what is called natural orientations, or I am saying this is oriented or directed curve. Okay. So that's exactly I have written. So if I have a curve C which is piecewise smooth in say some n-dimensional Euclidean space, parameterizations capital R. Okay, you take the parameterizations, and if t varies from A to B, then there will be a natural way of moving my point RT on the curve, and that natural way, the moving, that will give some directions, and that I am talking about what is called natural orientations. Okay, that is called the orientations. Now, there is a meaning of opposite curve. If you remember, in my last class I talked about, if I have a curve with some natural orientations, then I can talk about what is called negative of this curve. And what is the difference between the curve C and negative curve, which I denote as minus C? If C has a natural orientation in some directions, minus C has a orientation, it will be in the opposite directions. It traverses the same set of points, but the orientation will change. If C has a orientation, say clockwise, the minus of this curve will have orientation in the anticlockwise. Okay. So, let us see what is the definition of opposite curve. In fact, the definitions, if you remember, I have given in my last lecture. Okay. So, what is my definition? So, consider the curve C having a parameterizations RT, that is okay. The opposite curve, which I denote it as minus of C. So, what is the definition? It says that traces out the same set of points. So, that means given C with parameterizations capital R, what about the point it traced out by the parameterizations capital R or in the curve, minus C traces out the same set of points, but look, but in reverse order, and it has a parameterization, and you can also, minus C will also have a parameterizations, and what is that? I am writing that parameterizations in terms of the parameterizations capital R in the given curve C. So, that is what I am writing. So, minus C has a parameterizations, maybe you can say that this is R twiddle of T, right. So, because C is a curve, minus C is another curve. So, minus C will have a parameterizations, let it be R twiddle T, and that has a relations with the parameterizations capital R of the given curve C. And what is that? This should be R of minus of T, okay, and this time T will run from where? Minus B to minus A, okay. So, now if I have that one, then if C has a natural orientation in some directions, minus C will have the opposite directions, okay. So, first of all, you remember that the parameterizations are twiddle of the curve minus C, which is nothing but R of minus T. Now, if T runs over A to B, then minus T, or if T runs over, maybe I should say like that. So, look here, if T belongs to minus B to minus A, or in other words minus B lesser equal to T lesser equal to minus A, then what about minus T? That means B should be greater equal to minus T greater equal to A. That means minus T running over A to B, and this is nothing but R of minus T. That means whatever the points traces out for the curve C, same set of points traces out by the curve minus of C. That is the meaning. That means if T runs from minus B to minus A, then minus T runs from A to B, and R is acting, that means it traces out the same set of points, but the orientation will change. Why? Because if I have a parameterization R of T, so that means if I take T is equal to A, then what is my point? RA, right. So, it starts from RA and ends at RB, right. So, this is the one. And what about the reverse one? Look, so reverse one, it is a parameterization, so R twiddle. So, that means what is R twiddle of minus B, you see. So, T running from minus B, na? So, therefore, what is R twiddle of minus B, which is nothing but R of B. So, that means it starts from the point RB, and where it will end, which is nothing but R twiddle of minus A, which is nothing but RA. So, that means minus C starts from RB, ends at RA, whereas your curve C starts from RA and ends at RB. That means if you starts from RA, if you go in this direction up to RB, your minus C which starts from RB and comes at RA at the end point. Okay. That means if this is the natural directions, so minus C will have a opposite direction. It will trace out the same set of points, only the direction will change, it will be in the reverse directions. Okay. So, this is the corresponding parameterizations of my curve minus C in terms of the parameterizations capital R of the given curve C, which is R of minus T. This time T runs from minus B to minus A. So, one example I have given. So, for example, take a circle of say radius 2 in 2-dimensional plane. So, therefore, this is C, which is RT is 2 cosine T 2 sin T, T runs from 0 to 2 pi. That means it will have a circle of radius 2. Okay. So, this is 2 comma 0. And if I, as I said, it runs from T from 0 to 2 pi, right. So, therefore, at T is equal to 0, it will give you 2 comma 0, right, and then it will give you some natural orientation, natural directions. So, that means at T is equal to pi by 2, it will give you the point 0 comma 2. So, that means I am actually going in this direction, That is the natural orientations of C. Okay. Then the opposite curve minus C, you just define in this way. So, what is the parameterizations of minus C, which is r twiddle of t, that is I am writing this is r twiddle, or I am writing r, so it does not matter. So, in my this way you can have this r twiddle of t, and which is nothing but we see r of minus t. So, r t has a parameterization 2 cos t comma 2 sin t, which has replaced t by minus t. That means, this is 2 cos of minus t comma 2 sin of minus t. So, cos of minus t is cosine t, and sin of minus t minus 2 times sin t. So, that is the parameterizations of my opposite curve minus c, and you can easily see that at the point minus, of course, this time t running from 0 to 2 pi, here t running from minus 2 pi to 0. Now, at t is equal to minus 2 pi, okay. So, what is my r of minus 2 pi, which is nothing but, or r twiddle of minus 2 pi, same. So, what is this? This is actually will give you 2 cos of minus 2 pi, okay, and then minus 2 sin of minus 2 pi. Okay. But sin of 2 pi it will give you 0, and what is cos of minus 2 pi, it will give you 1. So, that means the point is 2 comma 0, right. Okay. So, that means you will start from here. So, now the direction will change, that means this time direction will be in this directions. For example, you take the point what is called minus 2 pi. So, that means again at minus 2 pi it starts from here, but this time what will happen, it will move in these directions, because directions will change. Okay. So, this is again at t is equal to 0, again it is a closed curve. So, therefore, again it will go in this direction, it will come back at this point. So, therefore, if C has the natural orientations in the anticlockwise directions, minus C will have a opposite direction, that means it should move in the what is called clockwise directions. This is the clockwise directions. Okay. Fine. So, yeah. So, okay, fine. Yeah, for example, so t is equal to minus 2 pi to 0. So, therefore, if I take t is equal to say what is this? This is minus pi by 2. If I take, then what will happen? This should be, I should write. So, that means r twiddle of say minus pi by 2, which is same as 2 times cos of what, minus pi by 2. Okay. Then what will happen? This should be minus 2 times sin of minus pi by 2. So, this should be what, 2 cos 90 what, cos 90 0, right. This is 0, and what will happen at minus 2, it should be 2. Okay. So, it says that the opposite curve denoted by minus c traces out the same set of points, but in reverse order, and it has the okay, this is the parameterizations I have given. Okay. So, you can just calculate it. Okay. So, this is the parameterizations, like if I have, so you take few points 0, pi by 2, pi, 2 pi. So, that means the way it will move in this direction, anticlockwise directions, you just check that if I take the parameterizations here, which is nothing but the parameterizations of my opposite curve minus c, the orientation you will have, you will see it will start from here, the same point 2 comma 0, but this time it will move in the opposite directions. Yes, that you can check it out. Okay, using take few points like minus 2 pi, then you can take, I think, yeah, okay, I think this will be minus 3 pi by 2, that is why the point is missing actually, I am here. Okay. So, minus 2 pi, I think this should be, you can check, I am not doing the full calculation here, maybe minus 3 pi by 2. Okay. And then you will see the point you will have, I think this point you will get. So, that means this point what, 0 comma minus 2. Anyhow, so this point should be, so this first one component will be 0. So, cosine of what is minus 3 pi by 2. So, that means this should be 0, and this should be sine pi minus 3 pi by 2. So, minus, so 2 sine 3 pi by 2, that means pi plus pi by 2. Okay. Yeah, you can check it. Oh, yeah, this will be correct. So, that means you just take at the point r twiddle of minus 3 pi by 2. It will see, you will have the point 0. You just check it, you just do it, calculate it, you will be able to get it. This should be 0 comma minus 2. Okay. Yeah. So, it will give you. So, that means the breakup is like that. So, you will have minus 2 pi, you will have 0. So, therefore, this is my minus pi, and this is what is called minus pi by 2 and minus 3 pi by 2. Okay. You just check it, you will get it. Okay. So, therefore, the main conclusion is that if I have a curve C having the parameterizations r of t, then I can have the notions of negative of my curve, which is minus c, and what is the directions of what is the relations between the directions of C and minus C? If C has a natural orientations or some directions, minus C will have the directions in the opposite way. It traces out the same set of points, but only the directions of minus C will be reverse compared to the directions of C. Okay, so there are a couple of things again I have written. So, direction or orientations. So, okay, so the first definition is that, so let C be a simple closed curve, a smooth curve or piecewise smooth curve in 2D or in R2 with say natural parameterization C is equal to RT. Then there is a theorem which is called Jordan curve theorem. Okay, so what is the Jordan curve theorem? It says that the points on any simple closed curve. So, therefore, if I have a simple closed curve C, say in 2-dimensional plane, the points on any simple closed curve C are boundary points of two distinct domains. What are the domains? So, first domains, one of which is the interior of C and is bounded, and the other one which is the exterior of C and which is unbounded. Okay. So, what is Jordan curve theorem? So, Jordan curve theorem says that if I have a say simple closed curve C, then the points on this simple closed curve C actually are the boundary point of two distinct domains. One is the domain bounded by that simple closed curve, that is the bounded domain, and another in the, that is actually interior one actually, and the exterior in the outside, that means the unbounded one. For example, you just take a simple circle, this is simple closed curve. Okay. So, now it is the points on this curve. Okay, these is points on the simple closed curve are actually the boundary points of two distinct domains. So, one domain is the interior, that is called the bounded domain, and another one the exterior. Okay. So, this is the exterior one, this is the exterior, and this is the interior, and this is actually the boundary point. Okay. So, by Jordan curve theorem, the points on any simple closed curve C are boundary points of two distinct domains. Okay. One of which is the interior of C, and it is bounded because this is the bounded domain. Okay. And the other which is the exterior of C and which is actually unbounded. Okay. What is my next point? If C is parameterized so that interior bounded domain, so that is another way of kind of looking at the directions. So, how I look at it? Suppose C is parameterized, that means it will have a parameterization say capital R, so that the interior bounded domain of C is kept on the left as RT moves around C. Okay. When T increases from A to B, then we say that C is oriented in the positive directions or counterclockwise directions or anticlockwise direction. What it says? So, I have a C, I have a parameterizations. So, now if T runs from A to B, then RT, of course, it should move along the curve C, right. But if it moves in such a way so that the interior bounded domain of C is kept on the left. Okay. So, I mean, for example, just think about the circle. Okay, that is the known one. So, now suppose I am starting, so RT, what is R of R is a parameterization, right. So, R of T is a point in the curve, that is my curve C. So, C, this is a point in C. Now, what I am saying is that if T runs from A to B, so RT should move in such a way so that the interior bounded domain of C always in the kept on the left hand side. That means, see, look, RT is there. Now, if I move in this direction, in this direction, in this direction, look, in the left hand side I will have this domain. So, the interior bounded domain always in the left. So, that means actually I am in what is called counterclockwise or anti-clockwise directions. Okay. Whereas, if I move in this directions, in this direction, see, in the left hand side what I will have? I will have the unbounded one. In the right hand side I have the interior bounded domain, that is called the opposite directions, that exactly I have written. You see, if C is parameterized so that the interior bounded domain of C is kept on the right. So, if I move in this directions, okay, in the right hand side interior bounded domain is coming. So, that means this kind of direction is called the negative directions or clockwise direction. In this way also you can have the what is called directions, whether it is clockwise or it is anti-clockwise. So, that means by Jordan curve theorem, if I have a simple closed curve, it is nothing but the boundary of two distinct domains. One is the interior domain bounded by this simple closed curve, another is the exterior domain, right. So, this is the boundary points. Now, what is the clockwise or anti-clockwise directions, it says that if T runs from A to B, RT moves along the curve C and it should move in such a way so that always in the left hand side I will have a interior bounded domain. If RT moves in this directions, if T runs from A to B, then I will say that actually I am in actually what is called counterclockwise directions or anti-clockwise directions. Whereas if I move or if T moves from A to B and RT moves in such a way so that in the right hand side I will have a what is called interior bounded domain, then I will say that it moves in the clockwise directions or negative directions. So this is the picture. So this is one. So if I have this one circle, if I move in this direction, so in the left hand side I will always have interior bounded domain. That means I am in the what is called counterclockwise or positive directions or anti-clockwise directions. However, if I have a circle, if I move in these directions, in the right hand side I will have interior bounded domain, and that is called the negative directions or clockwise directions. Okay, so that's another way of describing directions and orientations. Couple of remarks. What is remark? So first remark is that if a simple closed curve C in, again I am in two dimensional Euclidean space, is oriented positively. Positively means actually I am talking about the what is called natural orientations. Okay, so suppose it is oriented positively, then the opposite curve minus C, as I said, if C has one orientation, minus C will have the orientation in the opposite way. So therefore if C oriented positively, minus C oriented negatively. That means if C has a anti-clockwise direction, so that means anti-clockwise directions, that means minus C will have a clockwise directions. Okay, so that means if C is oriented positively, minus C oriented negatively. And another remark I have given is that if the orientations or parameterizations of a simple closed curve C is not given, suppose, okay, then it is understood that C is oriented positively. So that means if I give some problem or some say that okay, take this curve C, by default say some circle or say semicircle, whatever curve I will give, simple closed curve. So if there is no parameterization is given, by default it is assumed that I am actually talking about the positive orientation, or it moves actually anti-clockwise directions. Okay, so oriented, C is oriented what is called positively. So now I think once I have the notions of orientations, once I have the notions of smooth curve, so now I am in a position to talk about what is called vector line integral. Now if you just remember what is scalar line integral, if you remember that I have a scalar field or functions, and then if you remember, that means I have a partitions of the curve. Okay, so I make a partitions, and that actually coming from your parameterizations. You take a partitions of your interval A to B, it will induce a parameterizations in your curve, and that means that parameterization means I can break my curve into finitely many arcs, small arc Ck, and then what I have done, I am taking a point, I am talking about the scalar line integral, take any arbitrary point in the small arc Ck, then I am making what is called Riemann sum. That means the value of my functions, suppose you have a functions defined like say Rn to R, and suppose the domain of my functions contains that curve, that means what you have to do, take any arbitrary point in that small arc, that is the partitions of your curve C, and then you take the evaluations of your functions at that point times you have to have the what is called arc length of the small curve. Okay, and then corresponding partitions, suppose you have n many points in the partitions, you sum it up, make a Riemann sums and take the limit. So that was the definitions of scalar line integral. Now what is vector line integral? So let's start with a piecewise smooth directed or oriented curve. Now this time I am starting with a smooth or piecewise smooth directed or oriented curve in Rn. Suppose some C has a parameterizations and there will be a natural orientations will be there. Suppose some direction I will have. Now this time, as I said last time when I was talking about scalar line integral, that means I started with a scalar field. Now I want to talk about vector line integral. So therefore let capital F be a vector field Rn whose domain contains. So now this time I am starting with what is called vector field. Okay, that means now I am starting with a vector field in Rn with some domain. Of course it will have some domain, but the domain should contains my curve C which I started with, that means it is smooth oriented curve, that curve in Rn, and I am starting with a vector field capital F with domain D which contains my curve C. Along with that I am assuming that my vector field capital F is piecewise continuous and bounded on my curve C. So that means what are the assumptions? Let's start with a curve C, piecewise smooth or smooth curve, oriented, smooth oriented or directed curve in Rn, starting with a vector field capital F on some domain D subset of Rn to Rn, and D contains my curve C. Along with that, capital F, that is vector field, is piecewise continuous and bounded on C. If that is the case, let P be a partition. Now partitions, you know what is the notions of partitions, I already discussed in my last lecture. So C will have a parameterizations, and with that parameterizations capital R, if I take a partitions in the interval A to B, it will give a partitions of my curve C in finitely many subarcs, right. So let P be a partitions. Now again choose the point Pi star on the subarc say Ci of C. Now this time I will make a Riemann sum. So earlier in the scalar line integral I will have a Riemann sum, right. The value of the functions f at Pi star times arc length, right. Now this time what I will do, I will have the arc length part is perfectly alright, but what I will do, since I am starting with a smooth curve with some orientations, so therefore I will have the notions of what is called tangent vector. Of course, you see in the smooth curve I will have the notions of tangent vector, in fact unit tangent vector, right. So what I will do, so this corresponding this point Pi star in the subarc Ci, since it is a vector field, so this is the corresponding vector capital F of Pi star, it is attached at that point. So suppose this is my curve, okay, suppose this is my curve, at that point I have one, since it is a vector field, that means one vector is associated, right, one vector is associated there, right. And then of course since it is smooth, you will have the unit tangent vector, that means you have the notions of tangent vector, that means you have one vector attached, since it is a vector field at the point Pi star in the subarc. So suppose this is my subarc Ci, so at the subarc Ci, at the point, suppose this is my point Pi star, okay, in Pi star capital F is a vector field, that means it associate a vector at the point Pi star, which I denote it as capital F of Pi star. Then you have a notions of what is called unit tangent vector. What you have to do, you have to take the dot product, that means F of Pi star dot product with T Pi star, that will give you a scalar. Then you have to hit it with by what is called delta S. What is the delta S? This is nothing but, okay, I think this should be delta Si, okay, okay, I was there, maybe I just, let me see, I think it is I is there, yeah, I is there, okay. So it's, so this is delta Si. So I have written what is delta Si, it is the arc length of the subarc Ci, T Pi star is the unit tangent vector of the curve C at the point Pi star. So now I will have a Riemann sum, and then you just take a finer and finer partitions, and that if the limit exists, then that limit I am talking about what is called vector line integral, okay. I hope it is clear what is the kind of difference between scalar line integral and vector line integral. So for the vector line integral, you have to start with a smooth oriented curve in Rn, start with a vector field capital F whose domain contains your curve C, and then take a partitions of your smooth curve oriented curve C, you know what is the meaning of partitions, into finitely many subarcs, take an arbitrary point Pi star in that subarc Ci, make a Riemann sum. How do you make a Riemann sum this time? What you have to do, at Pi star you will have, since capital F is a vector field, there is a vector attached at that point Pi star. What is that? Capital F of Pi star. This is the vector attached at the point Pi star, and since I am dealing with a smooth curve, so at Pi star it will have a, there is a notion of what is called unit tangent vector, that I am denoting as capital T of Pi star. Then what you have to do, I have two vector, I am taking the dot product, and then what I am to do, with that dot product multiply the arc length of that Ci, which I denote it as delta of Si, make a sum I from 1 up to n, because n number of partition points are there. This is called the Riemann sums, and then I will say that if partition norm goes to 0, which is nothing but maximum of delta Si, if this is 0, that means if I take finer and finer partitions, if that limit exists, then that I will say that it is a definition of vector line integral, okay. Yeah, so this is the definition of vector line integrals. So the vector line integral of capital F over the directed curve C can be defined as, this is the right hand side. So make a Riemann sum, okay. So as I said, this is corresponding Riemann sum. If the norm of the partition goes to 0, if this limit exists, then I will say that this is the vector line integral of capital F over my curve C, and this is the notations, the integration over C capital F dr. We may write the vector line integral of F over the directed curve C this time as well, in this way also, integration C F dr. So this is nothing but what, F dot product or F inner product with T, and then I am denoting as ds. So like what is called scalar line integral, right. So that means the vector line, this is actually maybe next class I will talk about more on that. In fact, actually vector line integral, it is nothing but the scalar line integral, but this time what is my scalar field? This is the scalar field, inner product F comma T. So therefore this is the left hand side is vector line integral, right, integration C F dr, which is nothing but the scalar line integral of the scalar field, this one. That means this is your function. So that means F inner product T, this is the corresponding functions from Rn, some domain subset Rn to R, and I am talking about the line integral of this scalar field, and it is nothing but the what is called vector line integral. Okay, let me see. Yeah, okay, I think I should stop here. So just I have defined what is the notions of vector line integral. Of course, initially I discussed with the notions of simple curve, closed curve, smooth curve, then the notions of what is called unit tangent vector, then couple of definitions of orientations in two different ways, then given a curve, what is the negative curve. So after defining all those things, then I have defined what is the notions of vector line integral. Now vector line integral, you know, so instead of scalar line integral, instead of scalar field, you have to start with a vector field, you have to start with the oriented smooth curve, and then you have to make a Riemann sum, but this time Riemann sum will be little different, but at the point all over the I already discussed many times. First you have to take a partitions of your curve, and if partitions like Ci is the smaller subarc, then take any arbitrary point pi star, and at that pi star consider the vector associated in that pi star, that means capital F of pi star, and you have the notions of tangent vector. Take the inner product and then hit it by length or arc length of this subarc Ci, make it a sum, make it a Riemann sum, and if partitions norm goes to 0, then the limit, if the limit exists, then I will say that this is the vector line integral of capital F over C, and then it will be treated as the vector line integral of capital F over C, which is nothing but the scalar line integral of the scalar field. What is my scalar field here? This is inner product between F comma T, or dot product between F and T. I think in my next lecture I will talk about more on that with some couple of examples. So I think I should stop here. Thank you.